On the 18th of February 2026, a team of astronomers released an image that should not have existed. Buried inside the Perseus galaxy cluster, 300 million light-years from Earth, sat a smear of 4 faint stellar clusters with almost nothing around them. No spiral arms, no glowing disk, no obvious body of stars holding it together. And yet, something was clearly holding those 4 clusters in place because, without enough mass nearby, gravity would have flung them apart long ago. Scientists gave this object a name, candidate Dark Galaxy 2, or CDG2 for short, and the moment they confirmed what it actually was, the room went quiet. This was not a normal galaxy with a bit of invisible mass mixed in. This was a galaxy built almost entirely out of dark matter, with barely a handful of stars scattered across it like dust on a windshield. 99% of its mass, astronomers calculated, was something none of us can see, touch, or detect directly. It was the first galaxy in history ever discovered purely because of the pattern its star clusters made, rather than because anyone actually saw its light. And the telescope that helped confirm it was real, rather than a trick of the data, was Euclid, humanity's newest and most powerful dark matter hunting machine. To understand why this discovery sent a jolt through the astronomical community, we need to rewind about a century, back to when scientists first realized the universe was hiding something enormous from us. For most of history, humans assumed the night sky was all there was to the universe, a single collection of stars we now call the Milky Way. That assumption held firm until the 1920s, when American astronomer Edwin Hubble turned his attention to a smudge of light inside what we now call the Andromeda Galaxy. He noticed a particular kind of star there, one that pulses brighter and dimmer on a predictable schedule tied directly to how luminous it actually is. By timing that pulse and comparing it to how bright the star appeared from Earth, Hubble could calculate its true distance. The same way, you can tell a candle is far away because it looks dimmer than one held close to your face. The number he got back was staggering. The star was so distant that it had to exist completely outside our own galaxy. Overnight, the universe grew from 1 galaxy to billions. Hubble was not finished. Studying the light from these distant galaxies, he noticed their colors were shifted in a way that only makes sense if they were racing away from us, and the further away a galaxy sat, the faster it was retreating. This observation was so unsettling that even Albert Einstein initially refused to accept it, preferring to believe the universe was static and unchanging. Einstein had gone so far as to insert an extra term into his own equations, a fudge factor called the cosmological constant, purely to force his math to describe a universe that stayed still. Hubble's data eventually proved him wrong, and the idea of an expanding universe, and by extension the Big Bang, took hold. But there was a deeper problem lurking underneath all of this, one that would take decades to fully expose. When astronomers measured how galaxies moved and how fast the universe as a whole was expanding, the numbers refused to add up. Galaxies were not just receding from us, they were accelerating away, and acceleration requires energy from somewhere. When scientists tallied up every star, every planet, every cloud of gas we could actually detect with light, it accounted for a mere 5% of everything needed to explain how the universe behaves. The other 95% was simply missing from view. Roughly 27% of that shortfall got labeled dark matter, an invisible substance that clumps together and adds gravity without emitting any light of its own. The remaining 68% was called dark energy, a mysterious force pushing space apart at an ever-increasing rate. Neither has ever been directly observed. Both were essentially discovered through the gaps they leave behind in our equations, like noticing footprints in snow without ever seeing who made them. Explaining dark energy has proven to be one of the hardest problems in modern physics. Einstein's old cosmological constant got a second life as one candidate, the idea being that empty space itself carries energy that pushes outward, and the more space that gets created as the universe expands, the more of this pushing energy exists. Quantum physicists offered another idea, suggesting that pairs of particles are constantly flickering in and out of existence throughout the vacuum of space, and that in the brief moment before they annihilate each other, they exert an outward pressure. The trouble is that when physicists tried to calculate how much energy this process should generate, their answer came out too large by roughly 120 orders of magnitude, an error so enormous it has been called the worst theoretical prediction in the history of physics. A third idea, called quintessence, proposes a genuinely new force of nature, a field that varies across space and time and gently repels matter, though nobody has explained why such a field should exist at all. Nearly a century after Hubble's discovery, dark matter and dark energy remain almost entirely mysterious, defined more by what we cannot see than by what we can. Dark matter itself was not discovered through some grand theoretical leap. It crept into physics through a series of small, stubborn observational puzzles that refused to resolve themselves. Astronomers measuring how fast stars orbit around the edges of spiral galaxies kept finding that those outer stars moved far too quickly, fast enough that ordinary gravity from the visible stars and gas alone should have flung them off into deep space entirely. Something extra had to be holding those galaxies together, some unseen mass wrapped around them like an invisible cocoon. Later, observations of colliding galaxy clusters, most famously the so-called bullet cluster, showed something even stranger. A clear separation between where the visible gas was located after the collision and where the bulk of the gravitational mass actually sat. The gas had slowed down and piled up in the middle, exactly as ordinary matter should when it collides, while the gravitational mass had sailed straight through, mostly undisturbed. That separation is now considered one of the strongest pieces of direct evidence that dark matter is real and that it barely interacts with anything except through gravity itself. This is exactly the gap that the Euclid Space Telescope was built to close. Constructed through a partnership stretching across 23 countries, involving roughly 80 companies, 300 research institutes, and 3,500 people, Euclid launched from Cape Canaveral, Florida on the 1st of July 2023. Its job description sounds almost contradictory. It needed to be able to photograph vast swaths of sky in a single frame, while still resolving the fine details of individual, faraway galaxies, essentially combining a wide-angle lens with a microscope. Compared to ground-based observatories, Euclid delivers about 4 times the resolution and 15 times the sensitivity in near-infrared light, and it can detect objects hundreds of times fainter than what previous missions like Gaia have managed. After a journey of roughly 1.5 million kilometers over about 4 weeks, Euclid settled into orbit around a gravitationally stable point called Lagrange Point 2, joining the James Webb Space Telescope and Gaia out there. This location keeps the Sun, Earth, and Moon conveniently positioned behind the spacecraft at all times, which prevents their light and heat from interfering with observations, while still staying close enough to Earth for easy communication. Euclid carries 2 main instruments to accomplish its mission. A visible imaging system captures extremely sharp pictures in visible light, precisely mapping the shapes and positions of galaxies. Alongside it, a near-infrared spectrometer and photometer measures how the light from each galaxy has been stretched, which reveals how far away and how fast moving each one is. Combine those 2 data sets, and you get something remarkable. A genuine 3-dimensional map of the universe, stretching back roughly 10 billion years into the past. Over its planned 6-year mission, Euclid intends to survey about 1/3 of the entire night sky in this level of detail, creating what will eventually be the largest and most precise cosmic map ever assembled. That first light data release from October 2024 offered far more than statistics. Among the very first images were a striking view of the globular cluster NGC 6397, one of the closest such clusters to Earth, photographed in full for the first time in a single 1-hour exposure, resolving even its faint, sprawling outer stars in a way no other instrument had managed before. There was also a haunting new portrait of the Horsehead Nebula, taken in the same short window of time, showing the swirling clouds of the Orion star-forming region in enough detail to help astronomers hunt for hidden, planet-sized objects drifting freely through the gas. And there was Caldwell 5, nicknamed the Hidden Galaxy, because dust and starlight from our own Milky Way normally obscure it almost completely, finally revealed edge to edge thanks to Euclid's infrared vision cutting straight through the haze. Each of these images served a scientific purpose, but together they also announced something simpler, that a telescope had arrived which could capture both breathtaking scale and exquisite detail in the same single frame, a combination almost no prior observatory could offer. Euclid's very first science images, released in October 2024, immediately reshaped how astronomers thought about galaxy formation. In just 2 weeks of observing time, the telescope captured 260 separate exposures covering an area of sky 500 times larger than the full moon is seen from Earth, and that was only about 1% of its planned survey area. Inside the Perseus cluster alone, one of the largest known structures in the universe, Euclid photographed over 1,000 known cluster galaxies and more than 100,000 additional background galaxies in a single shot. Buried in that data, the telescope also revealed more than 630 previously unknown dwarf galaxies, tiny satellite galaxies so faint that older stars had always washed them out of view before. Finding them mattered enormously, because the way small, faint galaxies cluster around larger ones is thought to trace the underlying scaffolding of dark matter itself. If dark matter did not exist, galaxies should be scattered randomly and evenly across space. Instead, they clump together in filaments and knots, exactly as if some invisible gravitational skeleton were pulling them into place. One of the main techniques Euclid uses to actually trace that invisible skeleton is called gravitational lensing, and it comes in 2 flavors. The dramatic version is strong lensing, where a foreground galaxy or cluster is massive enough to visibly bend the light of a more distant galaxy sitting almost directly behind it. When the alignment is close to perfect, the light gets bent equally in every direction, producing what is called an Einstein ring, a complete glowing circle surrounding the foreground object. These are exceedingly rare, requiring an almost impossible cosmic coincidence of alignment. But in September of 2023, an archive scientist named Bruno Altieri spotted exactly that kind of ring hiding in Euclid's very first calibration images, wrapped around a nearby galaxy called NGC 6505. It turned out to be one of the most detailed Einstein rings ever photographed, and it let scientists calculate the mass locked inside the foreground galaxy with remarkable precision, mass that included a healthy dose of invisible dark matter. Strong lensing events like that one are spectacular, but they are also incredibly rare accidents of cosmic geometry. Euclid's real bread and butter is the subtler cousin of that effect, weak gravitational lensing. Instead of one galaxy bending light dramatically enough to form a full ring, an entire cluster of galaxies subtly warps the light from countless galaxies behind it, distorting their shapes by amounts so small that no human eye could ever spot them directly. Astronomers instead compare huge statistical samples of galaxy shapes against what pure chance alone would produce, hunting for tiny, systematic distortions that only make sense if an unseen mass is bending the light passing nearby. It's a bit like trying to detect a whirlpool by watching millions of individual leaves drift slightly off course, rather than by seeing the whirlpool itself. Multiply that effect across billions of galaxies, and it becomes possible to build an actual map of where dark matter sits throughout the cosmos, layer by invisible layer. All of this scale creates an entirely new problem, though, one that has nothing to do with physics and everything to do with sheer data volume. Euclid's completed survey is expected to total hundreds of petabytes of imaging data. A single petabyte is 1,000 terabytes, and a typical home computer might hold only a few terabytes at most, meaning it would take something close to 1,000 ordinary computers strung together just to store what Euclid is collecting. That first 1% slice of sky released back in 2024 already contained roughly 100 million individual sources of light, stars, and galaxies both. No team of human researchers, however dedicated, could manually comb through numbers like that, looking for faint gravitational distortions or hidden clusters of stars. This is precisely why astronomers have leaned so heavily on machine learning to sift through Euclid's flood of data, training algorithms on smaller human-verified samples, and then unleashing them on the full data set. It has already worked spectacularly elsewhere in astronomy. One citizen science project in Japan had 10,000 volunteers manually classify 20,000 galaxies from Subaru telescope images, then trained an artificial intelligence on those classifications, which went on to correctly identify a further 410,000 galaxies with about 98% accuracy. Applying that same philosophy to Euclid's mountain of imagery is what eventually led researchers to something extraordinary hiding inside the Perseus cluster. The story of CDG2 actually began a year earlier than its public unveiling, with a statistical method rather than a photograph. In 2025, a researcher named Dai Li and colleagues at the University of Toronto developed a mathematical technique for spotting extremely faint diffuse galaxies, the kind so dim they barely register above the background noise of space itself. Rather than searching for a galaxy's glow directly, their method searched for something more subtle, unusually tight groupings of globular clusters, those dense, ancient balls of very old stars that typically orbit around a much larger and more visible galaxy. Globular clusters are almost like fossils. They form early in a galaxy's life and stick around largely unchanged for billions of years, and importantly, they tend to shine brightly even when the galaxy hosting them has faded into near invisibility. Searching archival Hubble Space Telescope images of the Perseus cluster, Li's technique flagged several candidate objects where globular clusters appeared to be clustering together far more tightly than random chance would allow, hinting that some kind of unseen galactic body might be holding them in place. Among those candidates was an object that would eventually be named CD2, made up of just 4 globular clusters sitting suspiciously close together, a number so small it made the case unusually difficult to prove. Having 4 globular clusters bunched together is intriguing, but it's not proof of anything on its own. It could, in theory, simply be a chance alignment, 4 unrelated clusters that happen to appear close together from Earth's vantage point without any real physical connection between them. To settle the question, astronomers needed to find actual light coming from the galaxy itself, however faint, spread out around those 4 clusters in a smooth, consistent glow rather than 4 unconnected points. This is where Euclid entered the story directly. Combining fresh Euclid imaging with the original archival Hubble data and additional observations from the ground-based Subaru telescope in Hawaii, researchers went looking for exactly that kind of faint, diffuse light, a signature that no simple coincidence could easily explain. What they found settled the debate. Extremely faint but statistically significant diffuse emission appeared wrapped around all 4 globular clusters. And critically, the shape of that faint glow looked essentially identical, whether it showed up in the Hubble data or the independently collected Euclid data. Two completely different telescopes, using two different instruments and two different observing methods, were picking up the exact same ghostly structure. That kind of agreement rules out imaging artifacts or random noise almost entirely. CDG2 was real, and it was the very first galaxy ever confirmed to exist, purely because of its globular cluster population, rather than through directly detecting its main stellar body first. The numbers that came out of the analysis were almost hard to believe. Under the most conservative assumptions, treating those 4 visible globular clusters as CDG2's entire population, researchers calculated the galaxy's total luminosity at somewhere around 6 million times the brightness of our Sun, with the globular clusters themselves accounting for roughly 16% of all the visible light in the entire galaxy. For comparison, our own Milky Way carries somewhere north of 150 globular clusters, dwarfing CDG2's tiny handful. And yet, despite being almost invisible, CDG2 clearly needed a tremendous amount of mass to keep those 4 clusters bound together instead of drifting apart under the pull of the surrounding Perseus cluster. When researchers calculated how much mass would actually be required, the number of stars needed to supply it fell wildly short of what they could see. Somewhere close to 99% of the galaxy's total mass, they concluded, had to come from dark matter, an extraordinary fraction that put CDG2 among the most extreme dark matter-dominated objects ever documented anywhere in the universe. It's ordinary matter, the stuff that makes up stars, planets, and everything we can physically touch, was likely stripped away over billions of years through repeated gravitational encounters within the crowded, violent environment of the Perseus cluster, leaving behind little more than a dark matter skeleton with a faint dusting of stars still clinging to it. CDG2 was not even the first candidate of its kind. An earlier object called CDG1 had been flagged using the same statistical method back in that original 2025 study, but follow-up observations at the time failed to detect any diffuse light around it, leaving its status genuinely uncertain. CDG2's confirmation immediately reopened that earlier case. If CDG2 really does contain barely any stars outside its 4 globular clusters, researchers reasoned, then CDG1 might be an even more extreme version of the same phenomenon, a galaxy so thoroughly stripped of stars that its diffuse light sits below what any current telescope, even Euclid, can detect. Some astronomers now suspect CDG1's globular clusters may never have properly dissolved into a wider stellar population at all, making it potentially an even darker and more elusive object than CDG2. Scientists are already planning further higher quality observations to settle the question, and the implication is unsettling in the best possible way. If 2 such objects exist purely by chance inside a single galaxy cluster, there could be dozens, maybe hundreds, of similarly dark, nearly starless galaxies scattered throughout the universe, hidden from view simply because nobody had the right tool or the right technique to notice them. What makes CDG2 so scientifically valuable is not just that it exists, but what it can teach us about how dark matter actually behaves under pressure. Galaxy clusters like Perseus are violent, crowded neighborhoods, full of gravitational tides, near collisions, and streams of hot gas that can strip a smaller galaxy of its stars and gas over billions of years. If CDG2 really did lose almost all of its ordinary matter through these repeated encounters while its dark matter halo remained largely intact, that tells researchers something important about how tightly dark matter clings to a galaxy compared to ordinary stars and gas. Some competing models of dark matter predict it should interact with itself at least slightly, subtly changing shape or dispersing under extreme gravitational stress, while other models predict it should remain almost perfectly rigid no matter what a galaxy goes through. An object like CDG2, stripped down to its barest possible skeleton, offers scientists an unusually clean natural laboratory for testing which of these competing ideas actually matches reality, without the ordinary matter clouding the picture the way it does in a typical star-filled galaxy. CDG2's discovery slots into a much larger pattern of breakthroughs Euclid has delivered since it began operating. Earlier in 2026, the telescope turned its gaze toward the crowded center of our own Milky Way, capturing images so detailed that scientists could finally distinguish individual stars in a region normally blinded by overwhelming light, work that will directly help future missions like NASA's Roman Space Telescope hunt for planets using a technique called microlensing. Around the same period, Euclid helped astronomers push into the very edge of observable time, discovering a dozen brand new ancient quasars in the universe's first 770 million years, nearly matching in a single year what earlier surveys had managed to find across an entire decade of painstaking searching. Each of these discoveries relies on the exact same underlying strength: Euclid's rare ability to simultaneously photograph enormous swaths of sky while still resolving impossibly faint and distant detail within it, whether that detail happens to be an infant quasar at the dawn of time or 4 lonely globular clusters marking the ghost of an almost invisible galaxy nearby. As of today, Euclid has completed only about 35% of its planned survey, with roughly 4 more years of observing time still ahead of it. If a single percent of sky, examined early on, was enough to turn up hundreds of new dwarf galaxies, an Einstein ring hiding in calibration data, and now the first confirmed dark matter-dominated galaxy discovered through its star clusters alone, it becomes genuinely difficult to imagine what waits in the remaining 99% of the map. Somewhere out there, hidden among the petabytes of starlight still waiting to be processed, there are almost certainly more objects like CDG2, more ghostly galaxies built almost entirely from invisible matter, silently orbiting within clusters we have already photographed 1,000 times without ever noticing what was really there. Dark matter has spent a century as an inference, a gap in an equation, a shadow inferred from the way galaxies move, rather than something anyone could point a telescope at directly. CDG2 changes that story just slightly. For the first time, astronomers found a galaxy that is, for all practical purposes, made almost entirely of the stuff, sitting quietly 300 million light-years away, waiting patiently for someone to finally notice the 4 faint clusters of stars clinging to its otherwise invisible frame. What comes next matters just as much as the discovery itself. Euclid's survey team has already begun applying the same statistical search technique that flagged CDG2 to other rich galaxy clusters within its growing dataset, hunting for the same telltale overdensities of globular clusters sitting suspiciously alone in otherwise empty patches of sky. Every new candidate that turns up will need the same painstaking cross-checking CDG2 received, comparing independent images from multiple telescopes to rule out coincidence before anyone can confidently call it a galaxy. It is slow, careful work, but it is exactly the kind of work Euclid was built to make possible at scale, turning what used to be a once-in-a-career discovery into something closer to a repeatable search strategy. Researchers are also hoping that spectroscopic follow-up, measuring the precise motions of stars within these faint clusters, will eventually let them weigh CDG2 with even greater precision, tightening that already staggering 99% dark matter estimate into a firmer number. There is something quietly humbling about all of this. A galaxy can apparently exist for billions of years, embedded inside one of the largest structures in the observable universe, orbited by thousands of brighter neighbors, and still remain completely unnoticed until a mathematician's statistical model and 2 space telescopes finally caught it in the act of barely existing. It raises an obvious question that nobody can yet answer. How many more CDG2s are out there, scattered through clusters we have already surveyed a dozen times, hiding in plain sight simply because we never had a reason to look for 4 lonely clusters of stars huddled together in the dark?